Hello and welcome to this lecture. So we've been seeing examples of solving linear equations and trying to connect it with the span and dimension. Let's continue now and let's change things a little bit, right? We're going to have 4 variables x, y, z and w, but only 3 equations, okay? So previously we had 3 variables, 3 equations. We had all sorts of interesting cases. Now we have 4 variables, 3 equations. Let's see what all type of cases we get, right? So let's look at that in this lecture, okay? So I'm going to go a little bit faster because you've seen many of the methods, but let's spend some time on this one. Okay, the usual method involves elimination. The first one, I eliminate the x's here, I subtract this, I hope I've done it correctly. And then I eliminate y again, third equation from the fourth equation, second equation, you get this. So that's it, you're done now, right? So z plus w is 1, y plus 2z plus 3w is 3, and x plus y plus z plus w is 3. Okay, so at this point you stop and you identify that there is one free variable w, right? You've got a free variable w. W you can take it to be anything. Once you fix w, you can uniquely solve for z, y and x. Okay, so that's what you observe here, and then you find that solution. So you put w equals u, and u could be any real number r. Then once you put w is u, z becomes 1 minus u, and then when you plug it back in here, y becomes 1 minus u, and then x becomes 1 plus u. Okay, you can check that all these things are true. Okay. Now again we know that this is a dimension 1 solution. In fact, you can separate it out nicely like this: 1 1 1 0 plus u times 1 minus 1 minus 1 1, and you see you have a dimension 1 solution in this particular case. And in fact, the number of solutions is infinite. Okay. So let's look at the column space. Again, the linear algebra view. You look at the span of 1 1 1, 1 2 2, 1 3 6, 1 4 7, right? The column span, the span of all the columns. If you do elimination like the way we did, you will see this is actually the span of 1 0 0 0 1 0 0 0 1 0 0 0, which is R3, okay, which is dimension 3. Okay. So notice when we had 3 equations, 3 variables, when the span had dimension 3, the solution had dimension 0. In this particular case, because we have another variable, the fourth variable, it seems like when you have dimension 3 for the span, your solution becomes dimension 1. There is one additional dimension available for you to exhaust and have a larger solution. Okay. So in this particular case, we had infinite solutions. In fact, you can argue whatever the RHS may be, you will have infinitely many solutions. Why is that? Think about it, because this has got a span R3. Whatever you may put here, I can satisfy it. I can have a vector, the span, it will belong to the span, right? It will belong to the column span. Whatever I put here, irrespective of even w, I can pick whatever w I want, because these things have rank 3 by themselves, I have this property. Okay, so this is an interesting little observation. You can think about it a little bit more. So you will have infinite solutions for any RHS. Compare with the 3 equations, 3 variable case, you will see the contrast here. Okay. Is that the only case? It turns out that's not the only case. If you change things around a little bit, if you notice here, I have changed this thing here, the 6 here became 5. Okay, that's my change here. Once I change the 6 to 5, you notice something slightly more interesting happens. The usual method gives you this type of equations, you do the elimination, and then you got a 0 equals 0. Okay, so now instead of one free variable, you have 2 free variables, and if you do the solution like I did before, it's a little bit more complicated here. You have to put w equals v I have put here, and z equals u. You should put w equals v and z equals u. So you will get y to be 3 minus 2u minus 3v, and then x, if you put it back, you'll solve. Okay, so this is a standard linear equation solution. I'm not going to do it in great detail, but I'll ask you to try it again. So you just put w equals v and z equals u and solve for y and x. You will get one vector, and then write it as a constant vector plus something into u plus something into v. Okay. So interestingly, we get a 2-dimensional solution. Okay. So that's an important observation here. The solution for this set of equations ends up being 2-dimensional because you got 2 free variables, right? So that's what you got. Now let's go and look at the span. If you look at the span here, interestingly, you will see that the span has dimension 2. Okay, 2 of these guys become 0. Previously only 1 became 0. Now 2 of these guys become 0, and you have a dimension 2 span. So notice now when the span reduced by 1 dimension, the solution seems to have gone up by 2 dimensions. Okay, so it looks like infinite solutions are there, but only if the RHS has a certain form, because the span here now is restricted. It's not all possible R3. It is only those of the form AB 2B minus A. Okay, So interestingly, you should be able to cook up a solution with a situation where you have no solution. Okay, so if you change the 9 to 8, you see that you get a contradiction 0 equals minus 1, because clearly this is not of the form AB 2B minus A, and it will have no solution. Okay. So we saw an example of 4 variables, 3 equations, where once again we had different situations. Again, the dimension of the span and dimension of the solution seem to be connected, and there are cases where there is a solution, there are cases where there is no solution. Okay, so it seems to be interesting. The final set of examples we're going to see will again change the numbers a little bit. We'll look at 3 variables, but now we'll look at 4 equations. Okay, so even here you will see some similar sort of cases emerge. Okay, so let's try that. 3 variables, 4 equations, right? So again, you do the same method, you try and do elimination here, and now you are stuck, right? So I mean, it's sort of done. Okay, you can do the subtraction here, y minus y, and then now you're done. You're not really stuck here, you're done. Okay, so you got 3z equals 3 and 6z equals 6. There is no inconsistency here, and from here you can get x, y, z to be 1, 1, 1. You're getting a dimension 0 solution. Okay, that's interesting. So let's look at the linear algebra view. If you look at the linear algebra view, the span of the columns is 1, 1, 1, 1, 1, 2, 2, 2, 1, 3, 6, 9. If you do an elimination, you will see, go to the reduced echelon form, you will see that this is the span of 1, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 1, 2. So if you multiply this by A, if you multiply this by B, if you multiply this by C, the last thing will become 2C minus B. So you notice here the span has dimension 3. So span has dimension 3 and the unique solution has a dimension 0. Okay. So in fact, there is a unique solution whenever the RHS is of the form A, B, C, 2C minus B. Okay. If you violate this form, you will not have a solution, right? Because as it is, the span is in R4, right? It's not R3 now. There are 3 vectors, but each vector has length 4. So the span of these columns now suddenly becomes R4. Okay. In R4, the span is only 3-dimensional. There are only 3 vectors here, it's only 3-dimensional. So it doesn't exhaust the entire R4, it's only a smaller set, and it's only those of the form A, B, C, 2C minus B. Now if it is R4, it will be A, B, C, D, right? The last one will also be anything you choose, but that's not possible. It has to be 2C minus B. So this is a 3-dimensional subspace of R4. Okay, so that's the span, and you get dimension 0 here. Okay, so this is the first example where you got a unique solution for 4 variables, for 3 equations and 4 equations and 3 variables. Okay. So now here is another case. What I have done here, I have changed the 12 to 13, and I have made another change also. Other than that, I have not made any change. I have made the 12 to 13, but from the previous answer, you know there is an issue here, right? So if you change this, you're getting 3z equals 3 and 6z equals 7, which means there is no solution. The first guy is giving you z equals 1, this is giving you z equals 7 by 6. You can't tally these 2 things, right? So there's no solution. And again, the span gives you the answer. If you have RHS which is not of the form A, B, C, 2C minus B, then there is no solution for this particular case. So notice how interesting things are happening. Maybe we need to dig deeper here, that's the suggestion, but let's look at that. Okay. The last case, again 3 variables, 4 equations. I've made few changes here. Instead of 2, 2, 2, I made it 2, 3, 4. Here it's 3, 5, 7, and this remains 3, 6, 9, 10. If you do your usual method of elimination, you will see that you will get y plus 2z is 3, and then 0 equals 0, 0 equals 0. Nice, isn't it? So these 2 things go away, and you end up getting a dimension 1 solution, infinitely many solutions in this particular case. Again, the linear algebra view is very interesting. If you look at the columns, they in fact become the span of just 2 vectors. Okay, the columns are 3, but the dimension is not 3, dimension becomes 2. Notice that when the dimension of the span reduced, the dimension of the solution increased, right? There seems to be the tension here, and that works out very, very well, but only when solutions are infinite, but only when the RHS is of the form A, B, 2B minus A, 3B minus 2A. You can check that that's true here. It's A, B, 2B minus A, and 3B minus 2A. If you change the RHS to anything other than this, then there will be no solution. You will get, instead of 0 equals 0, 0 equals 0, you will get a contradiction here. Okay, so that's also very, very interesting. Okay, so in all these examples, we saw a whole bunch of 3 by 4, 4 by 3 example. There are some general rules. It looks like the dimension of the span is important, and it sort of determines the dimension of the solution in some interesting way, right? But there's also this crazy case where there may be no solution, particularly if the span is not big enough, if it's not exhausting the whole space, then you may have a right hand side in these equations where you don't have any solution. So I mean, let's look at the general case, right? So far we've seen only small examples, 3 equations, 4 equations, 3 variables, 4 variables. Maybe if you look at the general case, we can do some better study and understand what is going on. Okay, so with this, we'll stop this lecture, pick up from here in the next one. Thank you.